Okay, hello. So this week's video is on a subject that's going to come back again in a later video on a more philosophical level, but it's an introduction to one way in which you can try and restrict your program so that something that someone shouldn't do when they're working inside your source code is something they can't do. So effectively, this isn't restricting someone who's using your final program in some way. This is restricting a developer working inside your program. And there are very good philosophical reasons why you might want to do that, both because it stops you making silly mistakes in your own code, but in some senses more usefully, if you're working as part of a development team, it means that someone working on another part of the code can use your code and not accidentally use it in a way that's incorrect. And what we're particularly going to be talking about is a concept that's often sort of called constness, which is related to the terminology in the C, C++ languages. But we're going to talk about it in three languages here. I'm going to introduce it briefly in Python, a bit about it in Fortran, and then we are going to move on to C++. And the C version in C is very similar to what's in C++, but obviously some bits don't apply. So, first of all, I'm going to start up Python. Now, there is no Python 4, there's Python 3. So, Python is not a language that helps you a tremendous amount here. Python allows you to modify pretty much anything on pretty much anything you want. And there's no way of stopping it entirely. But there are a few things you can use to give someone useful hints that you didn't intend them to modify this. And so the first and easiest one is to address the question that often comes up while learning Python. Why does Python have two different ways of having, a list of values? Because there's an actual list, but I can also do it with what I pronounce as a tuple. Some people pronounce it as a tuple. I'm not sure which is right. But they're equivalent. They're both containers. So I can do, A of 1. I've just reset A. I can do A of 1 and get the second element, because all the containers in Python start from element 0. Or I can do the same with B and I get the same element. But the difference comes not if I try and read an element out, but if I try and set an element. Because if I set element A of 1 to 14 and read it back, I've changed it to 14. If I try and do the same with B, my tuple, I get told it doesn't support item assignment. And that's related to the Python concept of mutability, which is quite a complicated one. But it's a useful thing to remember. If you're returning a list, set of connected values in Python, if you return them to somebody as a tuple and not as a list, then in order to change them, they have to completely throw away the tuple and create a new one, which might well clue them in on the idea that was something you never particularly intended them to do. You can also, in Python, make use of something that are called properties. So properties are something that you can attach to objects. So I'll just quickly create an object, which I'll just call obj here for simplicity. And I will create an initializer for it, which will set something called _value to the value 14. So self._value is 14. Now that underscore is a convention in Python. It doesn't mean anything, but a variable that's an object member variable like this that starts with an underscore is a hint in Python to a developer that this is an internal variable and you probably shouldn't be messing with it. It's not enforced in any way. Someone can completely ignore it and change it anyway if they want. But the underscore is a very common convention in Python, meaning this is a variable you shouldn't be changing. So here I'll use it. But if the internal variable is something you shouldn't be using, shouldn't be changing, well, it shouldn't be touching even. How do you get access to it? Well, what you do is you do what you do in some languages that enforce it, Java being an example. You would write getter and setter methods. But let's imagine here that value is something that's set up and someone shouldn't ever change it. Let's imagine, I don't know, it's a physical constant, say. So, well, you'd still write a getter, maybe, which returns that underscore value. But in a sense, this is now a bit ugly. In order to get that value, you would have to have all over the place, instance.getValue. And fine, that'll work. But the thing with properties is they allow you to make it more seamless. So what I will do here is I'll create value equals property, and property is a built-in part of Python, and it's effectively a function wrapper, and it takes two parameters. The first parameter of which is the function that should be called to get whatever it is that you're getting, and the second parameter is to set that as well. But if you don't want something to be settable, you just set that to none. And there we go. If I now create an instance of that object, I can now print the value, and I couldn't tell that I wasn't accessing a variable. I didn't have to put brackets here. In fact, if I do, it doesn't work because it just sees it as a value. But if rather than trying to get a dot value, I try to set it, it can't set the attribute. And that's because here I passed none. If I'd written another function that took a parameter and set self.value, I'd be able to do this. And that function would be called. And that has all kinds of uses. So for example, you can use that to only allow a value to be set if it's within a certain range and raise an exception if it isn't. But this is a sort of thing that you can do. And Python very much is the least helpful language you're going to find for this sort of thing, because I could always just do a._value is 20, and then if I access that through value without those brackets that I said didn't work, it's been changed because Python has no mechanism to actually stop me modifying anything. I could indeed have overwritten this value thing and it created a setter method if I'd wanted to. So that's Python. Okay, we're now going to move across and look at the same concepts in Fortran. So Fortran actually gives you quite a bit more control. So I'm going to create a module, which is a very common thing in Fortran. I'm going to call it test. And in this module, I'm going to put in the implicit none. That's always important in Fortran, or it can create variables that you didn't even know existed, and that causes problems. And I'm going to define an integer, which I'm going to call value, and I'm going to set it to 14 again. I'm now going to create a program, which I'm going to call demo, which uses test, also has that implicit none in, and then prints value. Okay, compile that, and I run it, and I get my value of 14 out. Fine. You'll notice here that I didn't bother with any kind of that thing like that underscore in Python. If I wanted this value to be an internal variable, you'd think I'd flag it in some way. But in Fortran, I don't have to, because I can also just put on here that this, if I can spell it, this is a private variable. And if I set that it's a private variable, when I come to try and compile it, it tells me that the value has no implicit type. Now, in some senses, that's an unhelpful error message because it doesn't tell me that the reason I can't use value is because it's here but private. But there's actually very good technical reasons why Fortran can't tell you that, because private variables don't have to be unique between modules. So if you were trying to use a value, it couldn't know which module you were trying to use the value from. So I can do that. But I can do other things as well. So for example, if I flag it not as private but as protected, I can compile it again and I can get the value. But if in here I try and set the value, that I can't do. And now it knows and gives me a more helpful error message. So a private value in Fortran is one that just doesn't exist outside the module where it's defined. I can use it inside the module, If I wrote some functions in this module, I could use them, but outside the module, I can't. A protected value is one that I can modify inside the module, but can't modify outside. And finally, I'll introduce the last one, which is parameter, which I couldn't modify anywhere. Okay, so there we go. That's variable control in Fortran, but Fortran also gives me something more helpful in a sense, which is I can also control what variables can be used for when I call functions, which is something you can't really do in Python at all. So I'm just going to create a subroutine which I'm going to call test, and it's going to take in two values which I'm going to call v1 and v2. And I'm going to put on this thing, which is for a Fortran program you've probably seen before, which is an intent statement. Okay, and in here, okay, I'm now going to write some code. I'm going to set v2 is v2 times 2, and I'm going to print v1. Okay, and I'm now going to do something that will actually work. Okay, create a variable, and I'm now going to call test with v1, and I'm going to give just a value, just 100. Now I'm going to do it the other way around. Otherwise, yeah, 100 and v2, and then I'm going to print v2. Compile that, and it fails because I've mixed my languages. It's not a valid Fortran print statement. Contains subroutine and subroutine. Let's see what the errors it's actually giving me are. Oh, yes, I've just mixed up the name. Because the module's called test, I can't have a subroutine called test as well. I'm going to call this one test S, so that the names are different. There we go. Let me change it where I call it here. Okay. So that compiles, it runs, and what I get printed first of all is this v1, which is 100. I get returned 17 times 2, which is 34, which is what I get. And just briefly to mention it, the reason I get that is because of the fact that Fortran is what's called a pass-by-reference language. So a variable that's passed into a subroutine as a parameter here can be modified inside the parameter and sent, and the value goes back out. And this is one of the reasons why intents are very important. Because there are circumstances where you just don't want a subroutine to modify a value, in which case that's where intent in comes in. You don't want to be able to modify a value. And there are also cases where talking about modifying a value doesn't make any sense at all. So, for example, if I change this around and also create here something which is v1, which is 100, I can happily pass v1, v2, like that. And it works, and I get out exactly the same. And I can switch these around, and I can call v2, v1. I'll change the answer. I'll get 17 and 200. No, I get 17 and 17. Yeah, I get 17. Yes, because I'm printing v2 again. I should print v1 now, and I'd get 17 and 200. Yeah, so that was just me printing the same variable twice. Fine. But the thing is, if I now change this around and don't have the value v1 here, I have 100, it won't compile. And the reason for that, of course, is because effectively what I'm doing is I'm passing in this value of 100 here. So this line here just becomes 100 equals 100 times 2. So I'm saying 100 equals 200. It's nonsense. Now, behind the scenes, it's a bit more complicated and to do with the computer storing things in special areas of memory. But the basic idea is if you've got a literal value like this, you can't act on it. You can't change its value. A literal value is a literal value, and it means what it means. So any instruction like this doesn't work. So as a consequence, you can only pass a literal value in Fortran to a parameter of a function that has intent in. I will say technically if you don't specify any intent that will work as well, but that's not considered good form in modern Fortran programming. So this is the other thing that Fortran gives you over Python. Not only do I have actual abilities to really control what someone can do with my variables, I can also say what somebody can do with my parameters to functions. And so from here, we'll move on and discuss C++, which gives you even more control. Okay, so in C++, you have probably the most control of any of the sort of mainstream languages over when things can be changed and when they can't be changed. And in part, that's because C++ needs it, and in part, it's a design decision, because C++ is very much philosophically designed around the idea of being used in development teams. So being able to prevent other people from changing things they're not supposed to be able to change is even more valuable when you're trying to stop somebody else who may not understand your code from doing things wrong than when you're trying to stop yourself from doing things wrong. And the idea in C and C++ is called constness, because that's the name of the keyword. Okay, so we'll just introduce the idea very simply again. So I'll create the main function, and I'll create a variable I, which I'm going to give the value of 15 to start with. And I'll print it. There we go. And I'll set it now to 25, and I'll print it again. Okay, and I then compile that, and I run it, and I get 15 and 25. Brilliant. But if instead of int I flag the int, the const int, it's now telling me that I can't assign read-only variable I. So this is now behaving like those protected variables that I showed in Fortran, or that property in Python. I'm fine reading it. If I take out this line, I can compile it, I can run it, and I still get my 15, but I can't change it. So that's what this const keyword does. It effectively flags something as being a constant value, something that can't be changed. And you can put const on lots of things. So, for example, I can have that's not constant, and I can create a const reference to I. And I can now modify I here, and that'll be fine. But if I try and modify it using that reference, it's now complaining on line 9, which is where I'm doing this setting of the reference. So const is a keyword you can use on quite a lot of things. And the important thing is here, it's a keyword. It is part of a variable definition. Whereas in Fortran, protected and private were part of a variable definition in a sense. In C++, this const always is. So for example, if I create a function here, demo, which takes a const int I, just have it print I again, because I can't think of anything else more interesting to use, but it'll then try and modify it and print it again. Okay, so I'll now get rid of everything except my definition of I here. And I will call my demo function. And once again, it refuses to compile because it doesn't like this line. If I take that line out, I can access the value and print it, but I can't modify it. Similarly, if I leave this modification in and take this const out, I can now modify it. And you get the same thing as well with those references. So pass by reference is very common in C++. This, of course, is one of the differences with C that doesn't have references. But I can do a const reference to a value I. And once again, it won't let me compile it so long as there is this value set here. Without that, I can compile it and run it. And this also gives exactly the same result as Fortran with regard to being able to pass literals, because it's no more meaningful to be able to pass, because the whole thing with a reference is you're passing a reference. It's like Fortran. It makes C, which is a pass by value language normally, i.e. you copy the value you're passing to a function when you pass it to the function. If you pass a reference instead, it becomes a pass by reference language, unsurprisingly. So exactly like in Fortran, this const here, I can replace my I here with just 15, the literal value. I can compile that and run it, and I get my 15. But if I take this const out, because we're now not going to copy the value 15, we're going to have a reference to it, it'll fail. Now, its error message is even more unhelpful than some of the Fortran ones until you know what it's talking about. And L values and R values are something we've had a video on in the past that are a bit of a mess. So const so far has acted pretty much the same way that it has in Fortran, and the even more restricted sort of things that I was able to show in Python. The big areas where const comes in C++ are when you start introducing the actual C++ object-oriented features. So I'm going to create a class that I'm going to call C1 again, out of a complete absence of imagination. Now, obviously, if you're a C++ programmer who's working with classes, you'll be familiar with public, private, and protected, which are the same keywords as we had in Fortran for variables. You can use them to restrict access to members of a class. So I'm not particularly going to go into those. They're very common. Although I will say protected in C++ means something very different to what it means in Fortran, which is an unhelpful element, I think, of Fortran's nomenclature there, because C++ used it first. But I'm going to talk about constness here in classes. And in particular, so I can have, for example, a const member function, a const member variable, but usually that would only be something you'd have as a static const, because, well, if it can't change its value, you only want one of them, so you want static. But not particularly going to talk about that. I'm going to talk about const members. So I'm just going to create an integer, and I'm going to create a function, call it demo again, just to keep it all simple, which takes an integer and will act on that. So at the moment, all that is a setter function, basically. No problem. I can quit that. I can compile it. Can I fix? I'll probably actually get rid of this function. We're not going to use it again. Okay. So I can now create C1 my C1, my C1.demo14, cout my C1.val, new line. Okay, that compiles, it runs. I can successfully set the value and read it back. But what about if I actually wanted to guarantee that a method wasn't going to change the internal members of a class. Now, on its own, that isn't particularly valuable because you just don't. But it's a hint to another developer that they shouldn't. And it's a hint to anyone inheriting from your class. I think it's more than a hint to anyone inheriting from your class that their member can't change a class. And it's very simple. I just use the const keyword again, and it goes here. There we go, between the definition and the implementation. And now I'm trying to assign to the member in a read-only object. So I can't do that anymore. And that's where const comes in C++ again. And that is also a very important element of const correctness, because, for example, if I now create my demo function again, I'll make that a function that will work. Yeah, actually, which is just a print. Okay, so that function will work, and I'll create my setter again as a non-const function that will work. Okay, so that will now work absolutely fine. Now I'll create my demo function here, which will take C1, const C1 reference. Okay, and that will call input.setter 14. Okay, but I will for the moment comment that out, and I will demonstrate that I can now call demo again, because I've changed it so that it isn't modifying an internal variable. But if I have this demo function here, which takes a const C1 and calls a non-const method, I can't compile it. Yeah. And basically, this is the thing. If you've passed a const reference or a const value of a class to a function, you can only call const methods on that class. So this is extremely powerful. You're now saying, I actually guarantee that not only can I not modify the member variables of this class, I can't even call a function that will modify the members of this variable. So const in C++ really does mean I cannot change this by any means. Now, I will say there are ways of getting rid of constness. There have to be for compatibility with C, in particular libraries, or just libraries in general that aren't const correct. So there is a way of getting rid of constness, but as a general rule, if you're doing that within your own code, you've broken your design. There is then just one more element of const that is worth going into, because it's one of the things that is tremendously confusing when you first see it, because the syntax looks absolutely awful, which is pointers to const. So I showed you briefly about const references, and const references, they look exactly like normal references with const in front. Const pointers, on the other hand, get more interesting. And this is actually an ambiguity in Fortran, because pointers have two properties. On the one hand, they have them as a pointer. A reference can only be a reference to one thing. When it's created, it refers to that thing, and it refers to that thing forever. A pointer, on the other hand, can be pointed to another variable. So you now have two things that you want to deal with, which is the pointer constant, i.e. I cannot point it to another variable, or is the variable that it is being pointed to constant? And in fact, you can have both. So just to note it down, I'll create two integers here, which are I1, which is 1 and I2, which is 2. And I will now create just an int star p. P is points to the address of I1. And I now print p, having dereferenced it, so I'll get the value of I1, and I'll now copy those with p2. Okay, that will compile fine, and I can do that. And similarly here, rather than pointing this to I2, I could do dereference p and set it equal to 45. And now here, if I print I1, you would see that I1, semicolon missing, I1 has changed to 45 because I've modified its value with a pointer. All normal C++. But now, you might think, if I put my const here at the start, I can't do that. I can't modify the value. And you would be absolutely right. I can't, because I'm trying to modify a read-only location. But I can happily still do this. I can take P and I can point it to I2. This should now be printing P, not I1. And that dereference P, hear me, that was just printing the memory hex address. Okay, so there we go, we get 1 and 2. So by putting this const in front, I can quite happily point my pointer to different places, but I can't modify the value. Now if I get rid of the const here and put a const instead here after the asterisk, I was complaining about two things. First of all, it's complaining because I do the redefinition, but also I'm now making a const pointer. I'm now making a pointer that always points to the same memory. So just like with a reference on the line here, I really should say what it points to. And now if I take those out, it'll compile. Mr. I1. There we go. It's now pointed to I1. It compiles and it runs, and I get I1 out twice. But now this line becomes valid again. I can dereference that pointer and modify its value. So what if I wanted to do both? Well, you wind up with this slightly unedifying looking thing here, which is I have a const pointer to a const int. It's one of those things, you sort of read it from the right in a sense. That's formally how a C++ compiler looks at it, although a lot of people can read it from the right. Because this is a const pointer to a const int, and I now could neither, I now can't compile it again, and I now could neither point the pointer to point to a new variable, nor could I change the value that the pointer points to using that pointer. Now you can go through as many levels of constness as you want. So in C++, you can have pointers to pointers, so you can quite happily have a constant pointer to a constant pointer to a constant pointer to a constant integer, or you can get rid of any one of those constants. It gets very messy very fast. And in modern C++, using pointers is not particularly common. Recommended anyway, it's actually very common. But this syntax is sufficiently unusual that it's very useful to see. And to a great degree, that's what this video is all about. It's making sure that you've seen all of the ways in which you can control access to variables. As I say, there'll be another follow-up video describing more about the idea of why you would want to, why it's valuable to use the tools that your language gives you to restrict what you can do as a developer. Because as a general rule, if you've gone through your code and used constant values all the way through a chain of functions, and you suddenly find you need to change that, something has gone quite wrong in your design somewhere. So, as a general rule, it's not actually a restriction. It's only a restriction if your design is broken in some way. I mean, it does definitely happen. Codes that have bubbled away and modified over many years. Something that once upon a time didn't need to change values now does. And it can be a real pain to go and remove all those consts. But usually you save more problems than you cause by doing this kind of thing. On that, I will just mention a couple of things I didn't mention as going through but are important, which is you can increase the constness of something. So if one function takes non-const values and then calls a function that takes const values, that's fine. Going from something that has no restrictions to something that has restrictions, absolutely fine. But once something's got a constness, you have to do something special in C or C++ to remove that constness to allow you to call a function that doesn't expect a const value. So const is actually in some senses contagious. It's even worse in Fortran, where once something is intent in, it cannot go ever to something that is intent in out or intent out. So once you've stated I cannot modify this, you literally cannot pass it to another function that might modify it. And that can be restrictive, but it's generally very helpful. There is one last thing I will just mention, which is in C and C++. It's not particularly common to see in actual code, but in some senses, actually, this const int syntax is actually backwards. It's there because it's really convenient for a human. It's a way humans like to think about it. But for more complicated uses of const, what you actually do would be something like int const j. And just to prove it, I'll compile that. Yeah, it's uninitialized, which is something, but there we go. But that compiles. So this syntax is one you will sometimes see. It's not common because it's not one that's actually terribly friendly for a user, and this does just mean, again, an int that is constant. But for more complicated uses of const in complicated types and things, this is actually the one that's consistent. This version, that's the one everybody uses, is technically syntactic sugar that makes it rather easier. So that's it for this week, and we'll be back next week with another video.